Everyone. I'm joined today by Scott Imlay, our CTO. Good morning, Scott.
Good morning.
And I'm Durrell Rittenberg, the Director of Customer Development. And today we're going to spend some time talking about simulation analytics and analysis of exploratory CFD data using Tecplot Chorus. And specifically, we're going to be evaluating results from the Highlift prediction workshop that was held last year.
That's right. This was a workshop sponsored by AIAA, the Applied Aerodynamics Technical Committee, and they were looking at evaluating the use of CFD to actually compute these high lift configuration flows, very complicated flows. So,
and in the context of Tecplot Chorus, this would be a very good example of an exploratory CFD case, which happened to be submitted by several authors. So we actually have a lot of results, but in general, it's very simple to use this as a kind of a barometer of what you might do if you're using or doing exploratory CFD and how Tecplot Chorus can fit in. Well, I'm on the subject. If you're interested, you can follow us with Twitter. We're on YouTube. We're on LinkedIn and Facebook. We'll come back to this slide, but it's on the front page of our website. So if you're interested, go ahead and take a look. Today, the agenda is somewhat simple. We'll spend a little time talking about the Tecplot Chorus concepts. In effect, what Tecplot Chorus provides, how it fits into the work that we'll discuss as part of the AIAA Highlift prediction workshop. We'll review the goals of that workshop. We'll spend a little time talking about how Chorus fits into it. And then we'll spend the bulk of our time really evaluating those results. And finally, we'll present the results from our analysis using Tecplot Chorus. So the primary drivers of why we ended up kind of where we are today has a lot to do with the availability of the low-cost computational resources. We've talked about this on several occasions, but basically CFD has, of course, matured as a discipline, and with it, computational resources have become much more powerful and certainly a lot less expensive, which has allowed people to, in effect, do things that they would otherwise do in the wind tunnel in CFD. And what we're going to show you is kind of how that pertains to the work in predicting lift using in the Highlift prediction workshop.
Right. The computers are growing. The power and memory in the computers is growing with Moore's law. It has been for a long time, doubling in power every 18 months or so, and that results in larger grids and faster run times, and that's what's really driving this. You can, once you get to a certain level of grid density, you can start looking at these complex problems and getting results in a reasonable amount of time.
Yeah, and there's certainly been a shift to the more high fidelity methods for doing performance prediction and optimization. So in the context of that work, and we'll kind of show you in a way a different way to do it, but really what we're seeing in the market is many people are using tools for physics visualization like Tecplot 360 and other tools, relying on a lot of scripts and other analytical tools to look at the derived quantities. Python certainly come up quite a bit recently, although I know some folks are using R and Jump would be two that come up with some frequency as well. Surrogate modeling, again, is an area where this is usually being done external to the field data. And finally, really what we're finding is that for the most part, people are exporting data in CSV files and or using Excel. Probably the most common engineering plotting tool in the world is Excel, whether we like it or not. So in that context, let's shift gears and talk about where the work we're going to talk about fits in the context of the paradigm of more exploratory CFD or production level CFD. Now in this case, when we think about the high lift prediction workshop, it's more exploratory CFD because we're really trying to model physical behavior, test data in particular, and get alpha maps.
Well, and you're looking in particular at how well the codes are working, which I think is a key feature of most of the exploratory CFD. Verification validation is exploratory, where you're running a series of codes, perhaps with different parameter settings, different flex functions, different turbulence models, and different grid densities. You want to do a grid resolution study, so you can really kind of tune what is necessary in terms of grids and other parameters in order to get a good solution. And that would then lead into perhaps a production CFD run where they may, now that they're, say, if they're doing this for a Highlift configuration, they may run a angle of attack sweeps and yaw angle sweeps and ranges of flap angles and all the things that you would need so that you could understand how the aircraft will perform in flight.
And that's kind of the key thing, is that we're seeing it isn't, as I've shown here, there's two boxes, but really there's a continuum. As you say, Scott, people go from exploratory to production level and start looking at trade studies. And even going back to the computational resources, what we're finding is that Moore's law is definitely in effect for the high-end, large-scale simulation. But even for smaller organizations, building a cluster internally that can handle this type of high-fidelity work is still quite feasible. So even small organizations now are applying high-fidelity simulation to production-level CFD.
Yes.
So with that, we'll transition into more of the Highlift prediction workshop.
So this is an example of a wing section for an aircraft with flaps down, like a transport aircraft you might see. And the key features of this are, well, it has multiple elements, and you have wakes that come off of these elements. For instance, the slat in front has a wake that interacts with the main wing section. The wake is within a pressure gradient from the main wing section, and it's also merging with the boundary layer in the main wing section. This is very difficult for turbulence models to handle. And then that then continues to the back, and you have yet another wake, which is merging with the boundary layer on the flap region. And it's important that these be accurately computed, because ultimately the maximum lift you can get from the wing, CL max, and the angle at which it occurs, alpha max, is dependent upon how much separation you get on that flap element in back. So this is a very complicated flow field that is a real challenge for the CFD codes, and this is why they put together the Highlift prediction workshop. And there was a large number of contributions to this, and it was very very interesting results. So
well, I would just, and we want to, of course, point out that this work was published, and the reference to the paper is down below, and this is work from Rumsey, Long, Striever, and Wayman.
Right. This is the summary of the Highlift prediction workshop in 2011.
Okay.
So the case that they actually ran was the trapezoidal wing. You can see on the right the experimental model. It's been tested at least 3 times. And they have data, experimental data that they could compare against. And they were running 2 configurations which had the same slat angle, but 2 different flap angles. Config 1 was a flap angle of 25 degrees, and config 2, or config 8, I'm sorry, was 20 degrees. And these are the main geometric configurations that were done. All the runs were utilized, one or the other. The data they took, and actually the extractions they took from the CFD codes are shown here. These little symbols on the wing section. You can see there was a series of chordwise pressure taps and on the wing, and then they actually duplicated several of those chordwise stations, or spanwise stations, the chordwise distribution of pressure and skin friction for extractions from the CFD codes. And this data is made available, and this is what we're using as the extracted data. We don't have the full 3D volume data at this point. Would love to get some of that for our data set.
Although we did run a few, or attempt to run a few of the grids to get some data, but we decided we'd stick to the final results, the CP results in particular.
Yes. Their goals were to evaluate the CFD technologies and codes for this particular configuration. We already mentioned they're using the NASA trap wing. The independent variables we're looking at here are typically angle of attack. They do angle of attack sweeps. They also look at the flap angle, as I mentioned. Another thing is there was a few runs that were their case 3 were 2 runs with brackets on. So most of them have the brackets that hold the flap in place. They're just ignored in the configuration 1 and 8, but they had a few that they included the brackets. We're not going to talk about that one specifically. There was a wide range of codes used. I think there was a total of 20-some submissions, with at least a dozen codes.
Yeah, 14, I think.
One of the key things they did was a grid resolution study. Everyone was supposed to do at least 3 grid levels. There were a range of grid types: structured, overset, unstructured. A range of equations sets that were solved: full Navier-Stokes, full Reynolds-average Navier-Stokes, thin layer Navier-Stokes. A few of the codes used thin layer, and there's even a lattice-Boltzmann submission. There's a wide range of turbulence models used, and there was even a couple that used transition models, even though that wasn't the intent of this particular study. And so in Tecplot Chorus, we have all of these things available to us, and we can filter on all of these parameters, and we can quickly compare the effects of turbulence models or the effects of grid density or the equations solved, or even which code you used. It's a very powerful tool for being able to evaluate this sort of exploratory CFD data set.
So that's a good transition. So what we want to do then in the use case here is we're going to attack this exploratory CFD case. We're going to take advantage of the descriptors, including the code, what type of grid resolution. We're going to use that to explore the metaspace, so to speak, and we're going to show you that we have ties to the physical quantities. And really this framework allows us to analyze the sensitivity to things like grid density, turbulence model, and we'll walk through how one can do that using the tool in an actual use case. So the goals of the case study will be to evaluate the grid convergence. We're going to assess the prediction capabilities of each configuration. We're also going to try to understand or identify the underlying cause of the variation between the solver and the turbulence models. And this requires that tie between, say, the integrated quantities, the metadata, so to speak, and other descriptors, and the field data.
Yeah, for example, I mentioned already that there's, of course, we're looking for CL max, so we're getting right up there where you have a lot of boundary layer separation. And so if you have 2 codes that give different values of lift, one of them may be developing a boundary layer separation earlier than the other, and you can see that in your skin friction data, and even in some cases in your pressure data, your coefficient of pressure data. And so that's where you can do that tie, and you can say, where is this actually happening? And you can look on the wing, and you can see, okay, I have some significant separation near the wing tip or the wing root.
Right. Yeah. So let's we'll use this as a transition. We're going to walk in and take a look at the data in Tecplot Chorus. To do that, I'll quickly get out of PowerPoint for a moment. I want to start with the data that we're looking at and give you an idea of how that data is currently formatted. And I understand that there's a slight lag between what I show you on screen and what you see on your screen, so I will do my best to go slowly enough so that you can see what's actually going on. First of all, the results themselves are in a series of directories. We have the CSV file. All this data came from the Highlift workshop. We have the forces and moments data, and each one of these is a submission. And under each one, there's actually a grid file, which is in a Tecplot DAT file. It just happens to be what they used in this case. And in addition, we have some CP data as well. Again, same thing. We're looking at each configuration, and these are PLT files that we extracted out for each individual case.
Right, and so this contains those extractions I mentioned. The chordwise extractions at multiple stations along the wing, and then there's the two spanwise extractions of pressure coefficient and the skin friction components of skin friction.
So to set up the project, to give you a little more context, here are the data. It's a simple CSV file. There's a couple of key parameters. So we have descriptors such as, does the data exist? I mean, it seems like a simple thing, right. But whether or not we have access to the data, what type of data, what type of grid, what was the grid resolution, type of grid, structured or unstructured. We have the turbulence model available, whether the brackets were on or off, or as you know, a lot of people ignored the brackets. We have the number of nodes, in this case in millions. And you can see we also have the CL, and this is for the entire wing. Also, some people actually broke that out by flap, by body, and slat. And finally, we have, at the very end here, we have links to where the actual data live. And you can see we don't have data for all of them. So this is what our CSV file looks like that we use to create a project. And that project we brought into Tecplot Chorus. And we'll start just by showing you this is that same table. And I'll actually include all the data here. And you can see we can very quickly say, for example, look at all the people who used CFD++. So we can quickly evaluate code, which is one of the variables we have access to, the type, whether it was node-centered, lattice Boltzmann, cell-centered, the grid resolution, coarse, fine, medium. Mm-hmm. We can also look at the grid system, and this is the actual grids. We had different unstructured grids, TETs, hexes, whether or not the grid was unstructured, structured, as I said, and then the turbulence model. So all these things are available to us to, in effect, kind of zero in on what we're most interested in. Okay, so this is the data. What we want to start off with, though, is just taking a look at some of the results that actually do have data and looking at the system in general. And so I'm going to show you, we have already set this up. What we have here is we're looking at the entry number, and each entry number represents a different configuration that was submitted based on a different code, different grid. And we're looking at, for each one, we're looking at each configuration as a function of alpha.
Right, and this is the spanwise, excuse me, this is the spanwise pressure distribution along the leading edge of the flap and the trailing edge of the flap. And so the leading edge is near the suction peak, and so you're going to see that a lower pressure there than at the trailing edge.
And just again, if you see there's a slight difference here, this is the unstructured grids. There's actually a second line that they extracted, whereas people used the structured grid, just looked at the stations at, say, 25, 85, 45%.
Yeah, and because of that, we see some funniness in a couple of the other plots that you showed before, the line plots. But yeah, so there are some slight differences between the unstructured and structured.
And we can, in this case, if we wanted to page through, for example, right now we're not paging by anything, and you'll notice that at this station, we're actually looking at almost like a Rubik's Cube. You're looking on one edge, and basically what this is showing us is that at this station, there's actually other cubes that are behind it. Mm-hmm. If there's only one solution, you only see one image. Like in this case, there's only one image available, whereas in this case, there's actually two images, which means that there's two cases at that alpha, but there's probably something changed in terms of the flap angle or what have you. So we want to start by just quickly evaluating the system. We're going to bring this back into focus. And we'll page by, say, the flap angle. So there are really two flap angles, 20 and 28. And you can see now we can walk back and forth in our system and try to understand what those changes are for each of the entries. So this is, again, the field data.
Right, and it's a they're a little small, I understand, but you can see that that's colored based on pressure. CP, and so you see a very low pressure near the leading edge of the wing, the suction peak, and that increases as you go up an angle of attack until a certain level at which it you actually move into the stall, wing stall, and at that point you start to see the pressures even out a bit more over the wing. The stall in this case is in the I believe it's in the 34-degree range.
Mm-hmm. Kind of consistent. The other thing, of course, is that we do have we're looking at CP at those two stations, the two span-wise stations, station 1 and 2, and you can see what the quantitative differences are here as well. And it becomes a little more pronounced when you look at the different flap angles.
Mm-hmm. Yeah, and if you go to 25 for a second, Durrell, and then you go down. This is showing the how the difference in pressure between the leading edge and trailing edges is narrowing as you go to an angle of attack of 37, indicating a significant stall on the flap.
Mm-hmm.
So separation.
And this is again one of the key things here is that we do have a tie-in to the data. So if we wanted to say look at all the results from 1 here at this particular span or this flap, we can view the information, view the data, so to speak, and we can bring that into our physics visualizer, which we may want to do. And you can see we actually have quite a few results here, and I'll just make these a little easier to see by tiling them. So we're doing something akin to what we did a second ago in Tecplot Chorus, but what's different here is that we're actually interacting then with the data, and that allows us to very quickly see kind of what's going on. So we can look, we know the entry number is not changing, but we may want to know what code was used and perhaps what the grid resolution was, and maybe even the grid type. And I'll just make this a little bigger so that it's more legible, and I'll synchronize those now. So you can see that we can evaluate these results in context, and again, going back to where we start to see stall, you can very quickly assess that. Now you can see that if we go back, we're actually looking at a series of results, and all of these results can be evaluated at the physics level. So this is the actual data that we brought in. You can see what the pressure looks like at this configuration.
Yeah, yeah. Go ahead.
Well, I was just I'll pop back into Chorus here. Mm-hmm. Okay, there's a couple of questions that come in, but we're going to hold off on those questions for just a moment. We're actually going to take a look at the grid resolution for a moment. So if we want to evaluate grid resolution, perhaps the easiest way to do that would be to look at a plot of, in this case, we'll look at, say, the number of field cells. And we'll look at, instead of entry number, perhaps we should look at alpha.
Grid resolution would be, so probably the number of nodes for, oh no, you're doing fields.
Yeah, so we basically are looking at the number of nodes here.
Yeah, and so we typically you want to look at something like lift versus the number of nodes. Yeah.
So, and number of nodes. Okay. And then we probably want to group these by, say, just the entry. So this is each entry. And because the grid resolution study was only done at certain angle of attacks, we're going to change alpha to a single value. And I believe the value was 28, Scott, is that correct?
Yeah, they did 13 and 28, but we can just do 28.
So we'll only look at 28. And the other thing is we only looked at one flap, correct?
Right. They just did 25.
So we'll also just look at, say, a flap angle of 25. So now what you see is just the entries. Now I have a filter here, has data. That means it has field data. I'll turn that off so we can see all of them. And we'll go ahead and sort these by number of nodes here. And you can see very quickly, these are all the entries that did a grid resolution study. And you can see some of them, we'll actually turn on lines and symbols so you can see the data themselves. So here you can see, for example, that someone did a very low resolution study, and their predicted lift isn't necessarily akin to what people were expecting.
Right. And then you can also notice that most of these actually do converge pretty well as you get to the higher number of field nodes. And so with the exception of one of these cases, for the most part, they are all converging reasonably well. Now, they don't necessarily converge to the same value of lift, but they are grid converging as you increase the number of increase the grid resolution.
So one of the things that you can see, someone asked who is green. That's fun.
Who is green?
I don't know. It's a good question.
Kermit?
Kermit the Frog, definitely. Let's actually evaluate each entry separately. So we'll go to a single value filter, and we'll walk through each entry. So you can see there are some where there are no data, because not everyone did the resolution study. But to answer your question, for example, we know that entry 8.2 was the one that seems like it's farthest off. And we can kind of walk through each of the different solutions. Now, we may actually say, well, what if we only care about people who looked at, say, structured grids versus unstructured? Well, you can go over here now and say, well, we don't want to look at experimental or other, and we'll get rid of the unstructured. And now we're only looking at those cases, and we'll go back to a range filter. Now we're only looking at the structured cases. Mm-hmm. So again, you can kind of dive in and really understand, in effect, what are the structured grids showing us.
Why don't you, going off script a little bit, but why don't you try doing that just based on turbulence model? I believe the green one, to answer the gentleman's question, the green one is actually one of the unusual turbulence models. So it'd be probably maybe one of the K omega models. Is
K epsilon, is there K omega?
Yeah, try that.
So
no,
okay.
So K omega, maybe SST model. Oh, you can just go through them and find out which one is. It's not
Spilotto Omeris. There it is.
There, it's one of the SST models, and they apparently had trouble. This was multiple entries for this same code, so it's not necessarily the code that's the problem. They had trouble with this particular turbulence model getting it to converge.
Mm-hmm. So again, one of the key things, and someone had asked about, what code was used. That's the other part that you can start to say, okay, well, maybe I only want to look at CFX results. Mm-hmm. And we can really kind of dive in, or CFD++, and I guess we'd have to move to a few other, but you can...
We're filtered on turbulence model. You need to undo that.
Oh, yeah. Oops, that's right.
Yeah.
So we really have a lot of flexibility to explore this design space. Okay, so let's see, there's a couple other questions that have come in, and I think, okay, someone had asked about the CFD codes. I think we kind of highlighted that a little bit. So what we've shown up to this point really is just how do you evaluate that grid convergence. And remember, for each one of these points, if we have data associated with it, we can actually take a look at it. As it turns out, you can see that most of the results that we're looking at in this view are, in fact, without data. So we'd want to go back and actually be more inclusive to try to see if we can pick up data. Or oh, there we go. Sorry. Okay, so these would be the ones with data. So if I wanted to take a look at, for example, this particular case, I can go right to that and look at the images and take a look at that CP. And again, it looks funny, as you might imagine, and it's consistent. If I go back to the XY line plot here for a moment, it is consistent in that it doesn't make sense that they should see this drop in lift. And they are seeing it with this particular grid, and it is consistent. They also have one way off here in the hinterlands. This would be another one where you want to view the image, and again, it's pretty clear that something's going wrong with this case.
Yeah, it's not clear exactly what, but you can, from this point, they could go back and do further evaluation and analyze what's going on with the code.
Okay, there's a bunch of people have asked, is this going to be available by video? Absolutely, this is being recorded, and I'll be more than willing to make that recording available soon after this webinar is over. Okay. Now we want to take a look at perhaps just the lift prediction in general. So let's go back and remove these filters real quick because we want to be able to look at all the data. And so we'll go back to a complete range filter. And what we're going to want to do is look at, see the lift surface. So what we're looking at in this view is field cells, field nodes by entry number, and that's not what we want to look at. We want to look in the y-axis perhaps at the lift surface. We want to use the entry number, and then perhaps on the, I guess my z-axis, sorry, should be CL. And the y-axis will actually look at alpha, because we want to look at the alpha sweep. So this is, in effect, we have the entry number. So this is from of the 20 some odd entries that were in the not the competition, but in the study.
Yeah. You can see that there seems to be two sets of data, and that actually represents, I believe we have both of the flap angles at this point. So you would expect to see lower lift for the lower flap angle. So you turn that off, so it's just, now we're just looking at the 25-degree angle of attack, and you see a better bunching together of your lift results. The other thing too is this is also, I believe, including all of our grid resolutions.
Mm-hmm. And this is all the grid resolutions.
So if you went to just look at the medium grids, you would probably get a more consistent variation as well. Mm-hmm. There you go. That's looking. So now you're seeing more of the actual variation between codes.
So what we'd want to do at this point is perhaps apply a surrogate model. So we'll actually add in our independent variables here, and now we'll show a surrogate model. And this shows, in effect, almost an average. And this is what you would expect. And if we go back, we can take a look, and we will in a moment, look at how this compares to the experimental data. But one thing to point out is as you get closer to stall, you can see that quite a few of these codes, in fact, diverged, did not predict the stall very well.
Yeah, that's of course where it gets difficult, or the most difficult. Even the lower angles of attack are difficult, but it's most difficult when you're up in have significant boundary layer separation. One of the interesting things might be to just try different turbulence models here. Maybe just look at the Splar-Dalmaris, and you might see some more narrowing of the data. Well, maybe not.
Not as much
There's
as you would
still
expect.
Significant differences.
And this goes back to, as you're going through and if you're doing exploratory CFD, one of the things that you might want to do, in fact, is say, well, okay, I know these cases, if I was actually going to use this for prediction, these cases don't look like they're effectively following what we would expect. We can make them inactive. And by doing so, by making them inactive, we actually are going to get a better fit to the data. And you can see that fit has updated based on those data. Bunch of questions that we have coming in, and so some of these I think are pertinent. There's a question about, can you separate cases with and without brackets? And the answer is yes. I believe we had somewhere in here brackets on and off. So if we wanted to get rid of all the ones that do have brackets, we can do that here.
Yeah. So you can see it's a fairly small change. There's just a few cases that go away. So there weren't a lot of cases run with brackets. Not every submission included the brackets. It was optional. And most of those cases did not have a major shift in lift.
Mm-hmm. There was a question about whether or not data can be extracted automatically. It really depends on kind of what you're talking about. In the context of what we're showing here, in fact, you could extract a lot of this data. I'm not going to go into it in great detail, but because we have a link back into Tecplot 360 as our physics visualization engine, you can run through a lot of extractions there.
Yeah, absolutely. If you have the the field data, the 3D data, or even surface data, you could be doing slices, for instance, and extracting slices from that data using a Tecplot macro. So what you would do is you would set up a Tecplot macro, and if you have consistency between your data files, you can run that in batch and run it on all of your data files, and it would give you a bunch of either data files or images that represent that slice.
And there was a very good question around, well, what if we have the perfect data set and we want to compare relative to that? How does one do that? Well, again, that's relatively easy to do if if we had the experimental, I don't know if the experimental data is shown in this case or not.
I believe it.
Let's see, no, I don't think we have any at this station. But in principle, the way that that would work is if you knew, for example, that we wanted to look at just these data here, and I'm only going to look at those images that have, or those data points that have field data associated with them. We can view the images of all of them, and if, for example, this were, say, the base case, and we'll just make sure that, let's see, we'll put the entry number, the code, the grid resolution, perhaps whether or not it had brackets, and let's say alpha. So we can set that as our kind of base case and do a difference from that. And what you can see is here are the pixel differences between that case and each subsequent case. So hopefully that kind of answers what you're talking about. Can you spread? Okay, so that was Linda Hedges that asked that question. Is the grid convergence analyzed only visually, or do you take into consideration the order of the scheme used by the solver? I guess
we're not. Yeah, that's something that eventually you would like to do, but we're not doing any analysis on that right now. But yes, actually, frankly, this data. I'm not sure it would be real easy to do that analysis. There seems to be a significant amount of scatter, but yeah, that would be something you would ultimately want to do.
How can I save files from my CFD code? That's an interesting question. Depending on your CFD code, this tool itself, Tecplot Chorus, if you're asking about compatibility, right now will basically load any data that Tecplot 360 can load. So that includes Tecplot, CFX, Fluent, CGNS, Plot 3D. I mean, the list goes on and on. So in principle, if you have data that is in a format that we can read, you can read it in to Chorus. The independent variables typically either are contained in a separate file, like a CSV file, or oftentimes we're seeing people using a directory hierarchy to indicate different independent variables. So,
if the independent variables, say angle of attack and flap angle, are in the directory tree names, the folder names, you can actually crawl their directory tree, and Tecplot Chorus will extract those information into that table you see. What we did here actually was to create a CSV file, so that was done independently.
Good question about the do we do statistical analysis to allow you to estimate confidence interval? That is something we're working on right now.
Yeah.
So that'll be available very soon.
We actually are going to show some slides of a box plot that is similar to that. It is a statistical analysis, but I don't know if it's this particular one you're talking about.
There's a question about the model settings in general, and I suspect you mean the circuit model we're using. We really have two circuit models. I don't know, Scott, if you want to explain the differences here.
Oh, sure. The quadratic response surface is really a function fit, a quadratic polynomial fit to the data. In this case, 4 dimensions. Kriging is a statistical technique that is more of an interpolative technique. It actually passes through all the points. May not be real applicable in this case when you have so much scatter in your data. It might look pretty bad in that region. So those are the two models we have, surrogate models we have.
And the intent is we're going to expand this to be open. In effect, you can apply whatever surrogate model you fancy for your analysis. So
right.
That's the intent. Right now, though, we're providing some simple ones so people can get started. Okay. There's a couple other questions. How lattice Boltzmann is comparing to with finite volume. Well, that's a good question. I guess we could try to take a look. There really weren't many people who submitted a lattice Boltzmann.
Well, there was one code.
One
I
code.
Believe.
So
yeah. So we could turn on lattice Boltzmann.
Well, we just
turn off the other ones first and see. Oh, you need to go up to the top and You know, well, it does take both. I'm not sure. Are we taking?
Well, I'm not sure how we're clipping it out, but nonetheless, in principle, one could do that. So.
I can tell you from looking at it before that it is not significantly different in this particular case. I don't remember, at least pre-stall. Post-stall, I don't remember exactly where it was, so I'm sorry about that.
Another question is, can you co-plot pressure distributions from different solutions? You mean in terms of taking a look at the data? Oh, you know what? I bet you that was what it was. It was the turbulence model.
Yeah, I think we were filtering turbulence models. Right. So now if you do just the lattice Boltzmann, you might see what's going on.
So there's the lattice Boltzmann.
Yeah, so you can see pre-stall it does pretty well, but post-stall it seems to be missing in this particular case.
Mm-hmm. In terms of the distribution in general, one thing that you could do in this context when you talk about co-plotting the pressure is we're going to go back here to just our table view, and let's make sure that we are looking at the right data. Okay, if we wanted to look at, these do have data, if we want to look at two of these simultaneously, and I guess they actually...
no, I don't think the data is entered yet.
There we go. Okay, sorry, we just had to grab the right one. So if we wanted to take a look at, say, these three and look at the pressure distribution, one can bring those data in using a template that we've pre-computed, or pre-created, pardon me. And we can go ahead and look at those data. So we'll give this a second. Loading that in, because it's a lot of data. So nonetheless, you can kind of look at that pressure distribution, but you can also look at the images as well. Same kind of thing. So this is that pressure distribution at the different stations. So hopefully that answers your question, Andrew, but I'm not sure if that's exactly what you're asking. And perhaps you can give us a little more detail. Okay, I think I've hit most of the questions. We have time set aside, but let's go ahead and summarize real quick here where we were, and then we'll open it up again to questions. So we kind of showed you how you can walk through and evaluate the results. And here are kind of a couple of things that we brought out of Chorus. Here's the grid convergence at an alpha of 28. And you can see what that convergence looks like. And it looks like, for the most part, grids above, I want to say that's what, 20 million or so?
Yeah, it's 20 to 40 million, it seems. They seem to be converged. Yeah. This is, as a high-lift configuration goes, this is a fairly simple one. Mm-hmm. So, you know, compared to a full aircraft configuration or something. Yeah. So 20 to 40 million is sufficient in this particular case, it seems.
Someone said, can I use this software coupled with a CFD-based design optimization software? That's a great question, Josso. I think it really depends on what code you're using, but I've actually had the opportunity to go through and use something like Model Center with this tool, and it worked quite well. So if you're using something like Model Center, I don't know what you're using for optimization, but should work pretty easily.
Yeah, yeah.
And I know that there's another group that perhaps offline I'll connect you with that's out in Seattle that's doing something very similar. And they use the Boeing optimizer in this case. So, okay, let's take a look. We have some questions, and we'll go to those questions in just a second. Here is the lift variation by entry, just again showing you we can export those results. And here's the variation by turbulence model, looking at Mentor SST versus the Spilart Almaris. And so that you can see then that you really can do this type of analysis. What we're going to show you now is some things that we're working on that will be coming later this year, hopefully, or perhaps earlier, depending on how one can analyze these same results, perhaps using a box plot approach.
And so the person who asked the question about the statistical analysis, this is an example of a statistical analysis. For this same data and overall the medium grid contributions. And so what we're looking at here is the statistics of median the two quartiles, first and third quartile, and then minimum and maximum values. And you can see there's 5 surfaces. The one that with the color contours on it is the median surface, but you can see surfaces above and below that surface as well. And also down below, we've taken the end values for 20 and 25 degrees, and you get the same plot, the box plot, line plot. And the shaded area in the center represents the central 50%. And this one also has the experimental data on it, so you can see how closely these contributions are actually coming to the data. And for the most part, they're doing pretty well compared to the experimental data. Same plot for the drag. We're not going to spend a lot of time on the analysis, but again, they seem to be doing fairly well on predicting drag, even up to and through the stall regime. A bit surprising, actually.
Okay.
And there's, I think there might be one more, but go ahead.
There is one more, actually, on pitching moment. Similar thing on pitching moment.
Yeah, the difference here is you can see that it actually, most of the codes do miss the pitching moment, the experimental pitching moment significantly.
Mm-hmm. Okay, before we hop on, we have a bunch of questions, so we're going to move into the Q&A here in just a second. Before I do that, again, if you'd like to follow us, we are on Twitter, we're on YouTube, and YouTube we have a whole bunch of different videos walking through different use cases, so if you're interested, go there. It would be a good place to start. We're also on LinkedIn and Facebook. So with that, boy, we have a bunch of questions, so let's get started. This is Q&A, so if you have a question, type it into the question dialog, and we'll try to get to it. To be aware of your time, I know we're at 47 or so, and we want to try to make sure we button this thing up at 55 after, so we're going to get through as many questions as we can. If we miss your question, we will try to follow up with you today with an email. Let's start with a question about how you can generate a CP versus X at a particular span location with a line plot, which each line represents a different simulation. That's actually not difficult to do. I don't know if we're going to have time to actually walk through that. What I can do, though, is we do have some examples of how to do that in a use case that we put together that I will fire off to those people who attended, and you can watch in detail how one does that. And it's really quite easy. Linda asked, how does this tool interface with other optimization tools like Model Center? In the case of Model Center, what you can do is set up the extraction. So when you set up your optimization, or if you're doing like a if you are doing optimization, you're probably looking at different geometries, but the one that I looked at in particular was trying to look at an alpha mock sweep. And so I did a simple orthogonal array and had it dump out the CFD files from Fluent in this case, and it dumped it out into a CSV file as well as a series of directories, and I was able to bring it into Chorus pretty easily. So I don't know if that answers your question specifically, but perhaps we can do that. There's some questions about, do we plan to have scripting with Python or R, if you want to talk about that?
Well, the scripting is certainly in the backlog, and it's going to be put in over the next few releases. I'm not sure exactly how long off the top of my head, but yes, we will have scripting. Will it be Python? I don't know that at this point.
Yeah. It's a likely candidate, though.
It's a likely candidate. Yeah. Probably not R, but even that's a possibility. They're still in the design process.
Mm-hmm. Yeah, and that would be very curious if those people who are listening, if you are using a particular scripting language that wasn't mentioned, perhaps if you could let us know.
Oh yes, contact us and let us know if you have a preference for a scripting language, and we would love to have that information. I noticed there's one about Y plus, the first cell Y plus recorded. Can you read that?
Yeah, it says, was the first cell Y plus recorded for each case? Was it held constant at the grid size or as the grid size changed?
You would have to go to the documentation for the workshop, but my understanding is that they designed it so that the medium grid had a Y plus near 1, and fine grid was a little finer near the wall, and coarse grid was a little coarser. And so, but it was not adjusted. So these are constant grid spacing. So, as the boundary layer developed, if it did not match what they expected during the grid generation, they did not readjust the spacing.
We have time for 1 or 2 more questions. So if you have a question that you haven't asked yet, this would be a good time. Boy, I see. Okay, there's
bunch of them.
bunch of them. There's a question about why they vary the turbulence model. It said, hey, I'm just asking a neophyte question. That's not a big deal. We encourage those and get very near, anywhere near quality results with different turbulence models. I don't know if you want to address that.
So they were, one of their goals was to determine which turbulence models worked best. Mm-hmm. And so they different groups, it was up to the group that was doing the submission, they chose which turbulence model they used. And sometimes they did multiple submissions with multiple turbulence models because they were doing the evaluation themselves, trying to decide which one worked best. This is a very difficult environment for a turbulence model because it has the, the wakes and the pressure gradients and boundary layer separation and all those things that curved streamlines, all those things that make it difficult. And so I think statistically, one of the best turned out to be the Szilard-Almaras model, one of the simpler models. But again, the best way to find that stuff is to go to the papers. There was a whole session at the 2011 aerospace, I think it was the aerospace sciences meeting, and they also had one, I believe, the previous year at the Applied Aerodynamics conference. So mm-hmm. there's a lot of papers out there describing the results.
There was a couple of questions about was the grid convergence analyzed only visually, or do you take into consideration the order of the scheme used by the solver? And I think that in the summary they talk about that a little bit, but we didn't talk about it here.
Yeah, we did not do any statistical analysis of it, and we didn't pull the order of accuracy. Do a Richardson extrapolation, for instance, is one way you pull in the order of accuracy, and Tecplot 360 has the capability to do Richardson extrapolation, but we did not take advantage of that.
Cool. Other questions? We're missing one?
Phoenix?
Oh, no, I think he just means Phoenix integration.
Oh, okay.
Okay. Well, I want to thank you. Oh, it looks like there's a couple more questions, but we can answer that offline. Thank you again, everyone, for joining us today. This recording will be available soon, and just because I think it's a good idea to bring this up yet one more time, I want to make sure that you're aware, if you want to follow us on Twitter or YouTube, feel free to do so. Thank you again for joining us, and we will make this recording available this afternoon.
Yes, thank you. It's lots of fun.